Ever think a little noise could actually make AI smarter?
Hmm, intriguing.
We're taking a deep dive into this paper from way back in 1993.
93. Okay.
Yeah, it explores this idea of using noise, like actual randomness,
Randomness.
to actually help neural networks learn better.
Okay.
Especially, and this is the kicker, when you're working with limited data.
Limited data. Yeah, that's always a challenge.
Totally. So it's kind of like, imagine trying to get a point across using as few words as possible.
Right. You choose your words carefully.
Exactly. You'd be super intentional. Turns out there's a similar principle at work here.
Oh, interesting. How so?
Well, sometimes adding a little bit of calculated noise can actually help these networks learn better.
It's counterintuitive for sure. Adding noise seems like almost like the opposite of what you'd want to do.
Right.
But that's what makes it so fascinating.
It's like, are we messing things up or actually making them better?
Yeah.
So let's dig into this. Have you ever heard of the term overfitting when it comes to machine learning?
Overfitting. Absolutely. It's a classic challenge.
Okay, so for our listeners, can you break down what overfitting is?
Yeah, so imagine a student cramming for a test.
No?
They memorize all the answers without actually understanding the material.
Right, they're just regurgitating information.
Exactly.
Yeah.
They might ace that specific test.
Yeah.
But try giving them a new problem, applying those concepts, they're totally lost.
They don't know what to do.
Exactly. And neural networks, they can fall into the same trap.
Oh, really?
They become masters at remembering the exact examples they saw during training.
Okay.
But they struggle to generalize, to apply what they've learned to new data.
So they're kind of stuck in a rut.
Yeah, like stuck in a loop. They keep repeating what they've seen before instead of being able to adapt and learn from new information.
So how do we get them out of that rut?
Well, this paper, it introduces a really intriguing idea called the minimum description length principle.
Minimum description length principle. That's a mouthful.
It is. We'll call it MDL for short.
MDL. Okay.
And it's all about finding the simplest explanation that still captures the essentials.
So don't overcomplicate things, basically.
Exactly. It's kind of like Occam's razor. Right. The simplest explanation is often the best one.
Keep it simple.
And this MDL principle, it acts as a safeguard, preventing us from building these overly complex models that might be really good at fitting the data they've been trained on, but terrible at generalizing.
So it's about finding that sweet spot between being concise, but also conveying all the important details.
Exactly.
Okay, so we've talked about the what and the why. Now let's get into the how. How does all of this actually work inside a neural network?
It all boils down to the network's weights. You can think of these weights like the knobs and dials that control how the network behaves, how it processes information.
So like fine-tuning a recipe, right?
Yes.
Small adjustments can totally change the final product.
Precisely. Even small tweaks to those ingredients can dramatically change the outcome.
That's a good analogy.
Finding that optimal set of weights, that perfect recipe, is absolutely crucial.
Makes sense.
For the network to actually perform well. So here's where it gets really interesting. What if, instead of trying to find that perfect set of weights, we shake things up a bit?
Shake things up? You mean like intentionally introduce some errors?
Not quite errors, but something close. We add a bit of calculated randomness or noise to the weights during training.
Wait, so we're intentionally making the network less precise?
It seems counterintuitive, right? But that's what's so fascinating about this paper. They found that adding this noise can actually help the network generalize better.
Okay, now you've got me really curious. How does making the network more random make it smarter?
Think of it like this. Imagine you're trying to have a conversation in a really noisy room.
Oh, I've totally been there. It's tough.
To focus on what the other person is saying, you need to tune out all the distractions. Right?
Exactly. You have to concentrate on the important information.
That's essentially what we're helping the network learn to do. By adding this noise to the weights, we're making it focus on the signal and ignore the irrelevant details.
So the noise acts like a training ground for the network, making it work harder to figure out what's important.
Precisely. It's like giving the network a more challenging learning environment, which forces it to develop more robust and adaptable representations.
Okay, that makes sense. But how do we actually introduce this noise in a controlled way?
Good question. The paper specifically uses something called Gaussian distributions to model this noise.
Gaussian distributions, those are the bell curve things, right?
Exactly. They're a way of representing data that's spread out around an average value.
So instead of saying a weight has to be this one specific number, we're saying it can fall somewhere within this range.
You got it. Some values in that range are more likely than others based on the shape of the bell curve.
So the network is basically saying, I'm not entirely sure what this weight should be, but I have a good idea of the ballpark.
Precisely. And this fuzziness, it actually helps the network avoid getting fixated on the specific details of the training data.
Because now it can't just memorize the exact values it saw before.
Right. It's forced to learn more general patterns that hold true across different inputs.
This is blowing my mind a little bit. So we're adding noise to the weights, but how much noise is too much?
That's where things get even more interesting. They use Gaussian distributions not just for the noise itself, but also to represent the weights themselves.
Hold on, you're saying the weights themselves are also represented by these probability distributions?
Instead of fixed values, we now have these ranges of possibilities.
Wow. Okay, so the whole network is basically working with probabilities now.
In a way, yes. And this probabilistic view of weights, it's a really powerful concept in machine learning.
I can imagine it definitely adds a level of complexity.
It does, but it's this complexity that allows the noisy weights idea to really work.
Okay, so we've got these noisy weights, this probabilistic view of the network. It all sounds very clever, but I have to ask, doesn't this make the math a nightmare?
You're not wrong. It definitely adds some challenges.
I bet.
When you introduce randomness into the network itself, you have to account for that randomness when you're calculating how errors propagate back through the network during training, a process called backpropagation.
Because now, instead of nice, clean values, you're dealing with these ranges of possibilities.
Exactly, and that can get messy. But the authors of this paper, they were clever. They developed some techniques to handle this.
So they found a way to make the math work.
They did, and they even provided a specific solution for a particular type of network architecture, ones with one hidden layer and linear output units.
So they found a way to make it work, but it's not necessarily a one-size-fits-all solution for any type of network.
Exactly. It was a great starting point, and it opened up a lot of interesting avenues for future research.
That makes sense, but let's step back for a second. We've been talking about adding all this noise, but we don't want the network to just go completely haywire, right?
Absolutely. We need some control over this randomness. We don't want it to become completely random.
Right. Too much randomness, and we're back to square one with a network that doesn't learn anything useful.
Exactly. That's where the idea of a coding prior comes in.
A coding prior, what's that?
Think of it like giving the network a gentle nudge in the right direction.
So instead of just letting the noise run wild, we're guiding the learning process.
Precisely, we're using this coding prior to say, hey, network, we want you to explore these noisy weights, but we have a preference for certain kinds of weight distributions.
So we're adding some constraints to the randomness.
Exactly. We're saying explore, but explore within these bounds.
Okay, that makes sense. But how do we actually define this coding prior? How do we tell the network what kind of weight distributions we prefer?
That's where it gets really interesting. Instead of using a fixed coding prior, the authors use something called an adaptive mixture of Gaussians.
An adaptive mixture of Gaussians. Okay, now you're just using big words to sound smart.
Maybe a little, but it's actually a really cool concept.
Okay, adaptive mixture of Gaussians. Break it down for me.
All right, imagine you're trying to find the perfect lid for a set of containers.
Okay, got it.
You wouldn't want to use the same size lid for every container.
No, that would be silly.
Right. Some need to be wide, some narrow. You get the idea.
Different lids for different containers.
Exactly. An adaptive mixture of Gaussians is kind of like having a set of lids that can magically change their size and shape.
Magic lids. Okay, I'm intrigued.
Instead of using a single fixed coding prior, we're using a bunch of these adaptable lids
Okay.
that can adjust themselves based on the data we're working with.
So it's like giving the network a toolbox full of different coding priors, and it can pick and choose which one works best for the task at hand.
Precisely. And that's what makes this method so adaptable, so powerful. It allows the network to find that sweet spot between adding enough noise to generalize better, but not going so overboard that it makes the learning process too chaotic.
This is all starting to make sense now. We've got the noisy weights, we've got the adaptive coding prior, but the real question is, does it actually work?
That's the million-dollar question, right?
Yes.
And the short answer is yes.
Yes.
This paper shows that using noisy weights, this adaptive coding prior, it actually outperforms standard techniques, especially when you're working with limited training data.
Which, let's be real, is most of the time.
Exactly. In the real world, we don't always have access to mountains of data.
So this could be a game changer for all sorts of applications where data is scarce.
Absolutely. Now, the authors, they tested this method on a pretty challenging prediction task.
Okay, what were they trying to predict?
They were looking at peptide molecules.
Peptide molecules. Refresh my memory. What are those again?
So these are chains of amino acids.
Right, the building blocks of proteins.
Exactly. And the goal was to predict how effective these peptides would be based on their structure.
Okay, so like predicting how well a key might fit a lock
Yeah.
based on its shape.
That's a great way to put it.
So how did they do? Were they able to get good results with this noisy weight approach?
They were. They had a really small data set, only 105 examples to train the network.
Wow, that's tiny.
And they compared their method against other techniques, things like weight decay, which basically prevents the weights from getting too large,
Okay.
and even good old-fashioned linear regression.
So how did the noisy weights methods stack up against these other techniques?
It consistently outperformed them. They achieved a significantly lower error rate on the test data, which suggests that this method is especially effective when data is limited.
So they figured out a way to train these networks on less data and get better results.
It seems that way.
That's pretty incredible. So it sounds like they cracked the code for getting neural networks to learn and generalize well, even when we don't have a ton of data to work with.
That's what it seems like.
Yeah.
But there's always a catch. The authors, they actually ran into an interesting situation that highlighted just how tricky it can be to balance simplicity with the need to, really capture the complexity of the data.
Ooh, a plot twist. Tell me more.
So remember that MDL principle, how the best model is often the simplest one.
Right. Don't overthink it.
Well, in one scenario, the model actually found a solution that was too simple.
Too simple. What do you mean?
It basically said, all these peptide molecules, they're basically the same. Let's just predict the average effectiveness for all of them.
And I'm guessing that wasn't the most accurate approach.
It wasn't. It prioritized simplicity over accuracy.
Interesting. So the model kind of took a shortcut.
In a way, yes. It decided to play it safe and sacrificed accuracy for the sake of being concise.
So what does that tell us about the MDL principle? Is it flawed?
I wouldn't say it's flawed, but it does highlight that simplicity can be subjective.
Yeah, what's simple to one person might be overly complex to another.
Exactly. How do we define it? How do we find that sweet spot between keeping things simple, but also making sure that our models capture the nuances of the real world?
It's a tough balancing act.
It really is, and it's something that researchers are still grappling with today.
Wow, that's fascinating. So this paper, it's not just about some neat trick with noisy weights. It's actually prompting us to ask some really big questions about learning and generalization.
Absolutely.
This has been an incredible deep dive. We've covered so much ground. We started with this idea of using noise to make neural networks smarter.
Who would have thought?
Right. We talked about Gaussian distributions, adaptive coding priors, but then we ended up in this really thought-provoking discussion about simplicity and complexity in machine learning.
It's all connected.
It really is. If there's one thing I want our listeners to take away from this episode, it's that sometimes a little bit of randomness can lead to surprisingly elegant solutions.
And never be afraid to question those long-held assumptions.
Sometimes the most groundbreaking discoveries come from the most unexpected places.
Truth.
And on that note, we've reached the end of our deep dive today. Thank you so much for joining us on this wild ride.
This was fun.
Until next time, keep exploring, keep questioning, and most importantly, never stop learning.